Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized via radiation from the Sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them.
When we talk about the global electric circuit, we are describing how electricity naturally flows throughout Earth's atmosphere. It can be generated by the interaction of solar wind with Earth's magnetic field, down to the electricity that individual clouds produce. Clouds that produce lightning in a thunderstorm, for instance, feed electricity into the global circuit also. They're all a part of the same system. While we have known for a while that electricity exists in the atmosphere, scientists are just beginning to understand the relationships between the different events that affect it. Could the amount of electricity in the atmosphere change the way clouds and storms develop? Could cosmic rays impact atmospheric electricity and the severity of winter storms? By doing basic research and creating computer models, scientists hope to answer these kinds of questions, and perhaps find answers to questions we haven't even thought to ask yet. We use math to represent natural phenomena, like how much energy Earth receives from the sun, and the weather that emerges as a result. By taking these things we know and translating them into a mathematical model, we can build a pretend Earth, a model to test things that we never could in the real world. Because models have to calculate so much math and can end up having so many variables, we use supercomputers. They help us predict what is likely to occur, from tornado-producing storms on the Great Plains to hurricanes forming in the Atlantic. Trying to create a model for the global electric circuit presents incredible challenges. First of all, studying the global electric circuit requires experts across many areas. Scientists who specialize in the uppermost atmosphere, solar wind, electromagnetism, chemistry, the physics of lightning, cloud formation, volcanic weather, and more. Secondly, the model is trying to encompass events that are a part of the global electric circuit on vastly different time and spatial scales, from sprites that appear for a few milliseconds to the 11-year solar cycle, or enormous events like gamma-ray bursts down to small particles that influence cloud formation and cloud electrification. And there's even uncertainties about how clouds are charged and how atmospheric conductivity occurs and breaks down. Scientists and mathematicians are trying to create a model that is flexible enough to handle all of those variables. It's a challenge, but there is no time like the present to seek answers to scientific frontiers. So what is the global electric circuit? It's a system that encompasses all of the electrical generators, currents, and TLEs in Earth's atmosphere. Because of observations, satellites, ground-based networks, and observations of electrical phenomena between clouds and the ionosphere, we know a lot more about Earth's global electric circuit that transverses Earth's upper and lower atmosphere, but we still have a lot to discover about the system. Basic research will help us get the answers we seek.
satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
What causes lightning? Lightning can be a beautiful and scary part of Earth's weather. You probably have seen lightning in a thunderstorm, but do you know why lightning happens? Lightning comes from electrical charges that build up within a storm cloud. Thunderstorms form when warm, moist air rises high into the atmosphere. This rising air is called an updraft. As air rises in the atmosphere, clouds form when water vapor in the air cools into water drops, called cloud droplets. Some cloud droplets freeze into ice crystals. These cloud droplets and ice crystals collide and form larger particles called graupel. As the ice crystals rise up, they collide with the larger and heavier graupel. These collisions result in positively and negatively charged particles. Ice crystals are small and light. The updraft carries the positively charged ice crystals higher and higher into the cloud. The thunderstorm cloud is mostly negatively charged, which causes a mostly positive charge to form on the ground. When these opposite charges become strong enough, there is an electrical discharge, an energy release, in the form of lightning. Lightning often connects the negative charges in the cloud to positive charges on the ground. This is called cloud-to-ground lightning. Why does lightning often hit trees, telephone poles, or other tall structures first? Trees and telephone poles are often the tallest objects on the ground. So, they are closest to the storm cloud and the first thing in the path of lightning. Lightning can also stay within a cloud or even travel between two clouds. This happens when lightning travels from a negative charge in one cloud to a positive charge within another cloud. This is known as intra-cloud lightning. By the time you see lightning in the sky, a storm is probably already underway in your neighborhood. But tracking lightning from space can help meteorologists predict the intensity of a storm. NOAA's GOES-R series weather satellites captured this imagery of lightning during a series of thunderstorms over the Midwestern United States. Imagery and information from these satellites help forecasters to predict the intensity of a storm and whether or not the storm will produce high winds or tornadoes. Find out more about Earth's weather at NOAA SciJinx.
So we're looking at the role of thunderstorms and electrified clouds in the global electric circuit. So a cloud doesn't have to actually be producing lightning to be electrified. And there's what we call a Wilson current that generally runs from the top of the cloud into the ionosphere and helps feed the global electric circuit. So in the typical thunderstorm setup, it's a source of charge. In the reverse setup, or the opposite polarity, it's generally a sink. So we're hoping to find some parameters of thunderstorms, like we're looking at the speed of the updraft and how much ice is in there, and we're hoping we can relate that to how strong or weak the current is.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles. Where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power.
you.